Thank you, Jan, and thank you all for coming. So this talk is based on a paper of the same name that I co-authored with Andrew Keane and Andreas Amann, published in Chaos. So the motivation behind this research was that time delay and periodic drive have both been fairly heavily studied individually because it occurs so often in many applications, such as engineering and so on. But the combination of the two features is a bit less common and so has received less attention. However, it does cause some very interesting dynamics, and so our goal was to try and shed a bit more light on them by studying the combination of time delay and periodic drive in the simplest, most elementary system possible, and hopefully develop some kind of method of studying the dynamics that might be applicable to more complicated systems. So in terms of how do we construct a very simple system with time delay and periodic drive, we're going to start with a system that just has time delay. So this very simple system here, x dot at time t is minus the signum of x at time t minus tau, with the initial condition that x at time 0 is known, and the times at which x at t was equal to 0 in the interval minus tau to 0 are also known. So the system is piecewise linear due to the signum function. The drive, the feedback, just switches between 1 and minus 1. That's the cause of a rather strange initial condition. Ordinarily, you'd need to know a continuous function over an interval for a time delay system. But in this case, we only need to know the sign of that function, and hence we only need to know when the function changes sign in the interval. So when we simulate this system to find stable solutions from initial conditions, we find that it's just got one stable solution with period 4 tau. You pass through x equals 0. The feedback takes tau time to change. It takes tau time to get back in the opposite direction, and then you have to repeat that to get back to the original state. So period 4 tau. At this point, we're going to introduce this definition of a p-or solution that has period p and or crossings from x negative to x positive. This helps us to identify different solutions as we go forward. So this rather simple system has a fairly simple behavior, but we're going to see what now it happens when we add a drive to it. So we're going to drive our system with a periodic drive that is period 1, forcing magnitude b, and we're going to maintain the same piecewise linearity with another signum function. But now we have much wider varieties of solutions available to us. So, for example, we have this 1-1 solution, period 1 crossing from x negative to x positive per period. And you can quite clearly see that the forcing is changing at every integer and half integer. It goes from negative to positive at every integer and back to negative at every half integer. Below that, we have a 5-1 solution, period 5, for the same parameter values as the 1-1. So that means that the system is bistable. It has multiple stable solutions existing at once, and the solution that the system converges to depends on the initial conditions. Bistability is very prevalent in the system. You can see that as well in this 4-2 and 3-1 solution that are bistable. And the 4-2 one is worth noting because it doesn't have symmetry across x equals 0. If you look at all the other solutions, they have the symmetry where if you flip them across x equals 0 and shift them by half of their period, they match up with themselves, but the 4-2 doesn't. And that's the case for all even period solutions in the system, as well as some odd period as well. But most of the solutions we're going to look at here are going to have this property that if you flip them and shift them by half their period, they will be symmetric. Finally, we have a 3-3 solution here, which now kind of starts to justify our p-or notation, because we have a 3-1, 3-3. They are quite different. Their behavior will prove to be very different, and if we didn't have a way of distinguishing them, it might be a bit confusing. So now that we know what solutions more or less look like, we're going to take a broader view in our parameter space to see what solutions occur. And so what we have here are a pair of period charts in the b-tau plane. We need to have 2 of them because of the bistability. So if we were to just simulate the system from initial conditions, from arbitrary initial conditions, then we would get unclear results in regions of bistability. So what we do instead is we sweep along up in B and then back down using the final state of one simulation as the initial condition for the next simulation. And what that does is it allows us to follow a particular solution for as long as it exists and is stable. And so you can see here that the different colors represent different period solutions. So we have as the dark blue for 1,1 and increasing in brightness as we go up, with the white indicating aperiodic solutions that don't converge to a periodic orbit. So one of the key features of the system that you can see is the presence of these Arnold tongues, these regions of the b-tau plane in which the feedback and the forcing synchronize to produce a periodic solution. The Arnold tongues show some rather interesting features. The first one is that they narrow to points along their length, dividing into a chain of smaller tongues. And in each of those tongues, the OR value for the solution is different. So for example, for this 7-1 tongue, or the period 7 Arnold tongue, we have a 7-1 tongue, 7-3 tongue, a 7-5 tongue, and a 7-7 tongue. There's also some repeating patterns as well in the tongues themselves. So for example, these 9-1, 7-1, 5-1, and 3-1 tongues, they all have the same shape with this straight lines for b less than 1 and curves for b greater than 1. But there are some differences. So the 3-1 tongue has these 3-3 tongues outside that the other ones don't have. Whereas the 1-1 tongue, it only has the same shape for b less than 1, but then covers the rest of the b-tau plane in a way that the others clearly don't. And then when we sweep back downwards in B, the 1-1 solution has this very rectangular boundary that's quite unusual. So we're going to focus the rest of the talk on the similarities and differences between these P1 tongues to see what's going on. And when we look at those bifurcations, of course, the bifurcations might be a bit unusual because this, of course, is not a smooth system. So that's, of course, where the border collisions arise in the title of the talk. So what we're going to do now is we're going to try to understand the system a bit more by focusing on the 5-1 tongue. We're going to try to figure out what happens to the 5-1 solution at the boundaries of the tongue and why it's the shape, why does it have this symmetry across tau equals 5/4. And part of what we're going to do in order to help with that is we're going to look at how we use symbolic dynamics to study the system. So what we did was we came up with a more precise definition of a solution than our PR notation by defining a solution as a sequence of events. So our events, we had 6 different event types. So for example, a D event was a change of forcing from negative to positive. H event was a change of feedback from negative to positive. And a Z event was a change of the solution from negative to positive. And if you stuck a bar over one of those symbols, then it meant the opposite transition. So D bar, transition of forcing from positive to negative. And how this helps us with the 5-1 solution is that we can note that there's actually 2 different sequence representations for the 5-1 solution, depending on whether you're in the top half of the tongue or in the bottom half. And this just occurs because of a change in the sequence when the delay between a crossing of 0 and the change of feedback occurring swaps with a change of the forcing. And so that gives rise to these slightly different sequence representations. But what you note about the 2 solutions is that they have this symmetry to them across tau equals 5/4. And so whatever happens in one at a certain distance from tau equals 5/4 will happen in the opposite direction of the other one. And that gives us the symmetry across tau equals 5/4. So now let's see where the boundaries are coming from. We're going to not use the sequence representations too much because they're so hard to say. But just keep in the back of your mind maybe that these sequence representations tell us a lot about these solutions. For example, each one is going to have different existence and stability conditions, and it's going to be worth keeping track of. So let's start looking at the 5-1 solution and see what's happened to the boundaries. So here's the 5-1 solution for b less than 1. As we approach the boundary, this change in forcing, marked by a triangle, gets closer and closer to x equals 0. If it was to cross x equals 0, that would change the symbolic representation, and we'd have a solution that looks like this, which we never actually observe through simulation. And so when we move closer and closer to the boundary, these two solutions will converge to each other and then vanish at the boundary of the tongue. So in order to figure out why this is the case, we're going to look at Poincare maps, because we know that if we build a Poincare map on a periodic solution, then the fixed point of the Poincare map, if that fixed point is stable, then the solution itself is stable, and the same for instability as well. So when we construct a Poincare map on the 5-1 solution, what we're going to do is we're going to say that this is our fixed point. We're going to construct it that way. We're going to call this point XD because it's a D event here, a change of forcing from negative to positive. And we notice three key things about it. The first thing we notice is that the trajectory of the solution is different for these two solutions, which means that the map is going to have to be different for whether or not we're at XD greater than 0 or XD less than 0. Because of that, there's going to be a border at XD equals 0 such that the map is continuous across the border, but it is not differentiable at the border. The second thing we're going to recall is that the solution has this symmetry where if we multiply by -1 and shift across by half the period, then it's going to be the same thing. And because of that, when we're building our map, we're not going to map from here to here, a full period ahead. We're going to map from here to here, so half a period ahead and flipped across. It's more or less equivalent and more appropriate. The final thing that we notice is that the map is one-dimensional. And the reason for this is that when we're going from here to here in our map, we need to know when all of these changes to feedback and forcing occur along the way. The forcing is the easy bit because it happens every half period, but the feedback is harder because we need to know when we cross x equals 0. In this case, it's easy enough because there's no changes in feedback and forcing between our current position and the crossing, so we know exactly where this point is, so we know exactly where this changes. So when we construct our Poincare map, what we find is we have two fixed points. We have an unstable fixed point for XD greater than 0 for this red solution, and a stable fixed point for XD less than 0 for the blue solution. And they will converge in a border collision saddle node bifurcation when we get to the boundary of the 5-1 tongue. And if you look at this plot, you can see the symmetry in tau of the tongue as well. So when we solve for XD equals 0 in our map, what we get out is these two lines here, showing that the 5-1 solution undergoes a border collision saddle node bifurcation of periodic orbits along those lines. But then what about b greater than 1? You'll note that this solution doesn't exist for b greater than 1. But let's look at the 5-1 solution for b greater than 1. It's worth noting that these two blue solutions are actually the same sequences. It's just as b changes, they look very different. And now we note that the triangle mark is far away, but the point marked by the circle is getting closer to x equals 0 as we approach the boundary. If it crosses the boundary, we no longer have a 5-1 solution. We have a 5-3 solution. Again, exists within the 5-1 tongue, but is never observed. So once again, we'll construct a Poincare map using this as our fixed point. Once again, it's got a border, we use symmetry, and it's one-dimensional. And now what we get out is another border collision saddle node bifurcation, but again for these 2 points. And when they approach 0, where the sequence representation would change Instead, we have a border collision saddle node bifurcation, and that rounds out also the bifurcation for our BLS1 representation, because what we find is that the 5.1 and 5.3 unstable solutions are actually the same solution, but just perturbed by a change of the sequence as they go through b equals 1. And once again, we have the symmetry. When we solve for xt equals 0, we get out these curves. And this can be applied to a lot of the tongues in the solution, in the b-tau plane. The 7.1 and 9.1 tongues behave exactly the same way. But we can note that the 3.1 tongue doesn't. It's got these border collision saddle node bifurcations for b less than 1, but for b greater than 1, it doesn't happen. And instead, we have this weird cutout here in this 3.3 tongue, where thanks to our symbolic representation, we know it exists there, but we don't observe it. So let's see what's going on there. So once again, we come back to our Poincare maps. When we construct a Poincare map for the 3.1 and 3.3 solution for tau less than 3 over 4, we're going to treat them separately. We find that there's only one stable fixed point. It starts out at xt greater than 0 for the 3.1 solution, and then drops down to xt less than 0 for the 3.3 solution without changing stability, which matches, of course, the 3.3 solution itself. However, for tau greater than 3 over 4, it's quite different. And so let's take a closer look at that. So here's our 3.1 solution. Once again, we want to get from here to here, which means knowing when this feedback occurs, which means knowing when this zero crossing occurs. Because we know when this change of forcing occurs, we can just get straight back there, so we can calculate this point, and so one-dimensional. However, when we cross into 3.3, that's no longer the case, because these two feedback changes between our current position and the zero crossing that causes this change of feedback. And so we can't calculate this from this. So we have to be given the change of feedback as well. And so that means the map will be two-dimensional for the 3.3, but only one-dimensional for the 3.1. So we embed the 3.1 one-dimensional map into a two-dimensional one, stitch them together into another map with a border. And when we analyze that, we find that there is a stable fixed point for xt greater than 0, matching the 3.1 solution. But for the 3.3 solution, it's not quite so simple. What we find is that the map undergoes a Neymark-Sacker bifurcation for b equals 2.6, more or less. And so it's stable for b greater than 2.6, but then becomes unstable and generates a closed invariant curve as it passes through that line b equals 2.6. It's a bit like a Hopf bifurcation would be in a continuous system. And so because the map undergoes a border collision, a Neymark-Sacker bifurcation, the solution itself undergoes a torus bifurcation. And now when we bring that to our border here with the 3.1 solution going into the 3.3, we have the same thing happening, but basically when we pass through the border, the dimension system increases, the fixed point becomes unstable immediately, and we start to create that closed invariant curve again. So we have a border collision Neymark-Sacker bifurcation this time. And this works out also experimentally when we look at the simulation of the solution itself, not just in the map. So that means that along this line, we have a border collision torus bifurcation, and along this line, we have a torus bifurcation of the 3.3 solution. And in this region, it's unstable, and you kind of see that as the feedback is starting to mess with the smooth and stable 3.3 solution. But once you increase the forcing enough to overpower the feedback again, it restabilizes. I'm a bit short of time, unfortunately, to fully explain the 1.1 solution, but to boil it down, the map on the 1.1 solution has a variable dimension that increases as tau increases So every multiple of half, the dimension goes up, because in order to calculate when the crossing, when the feedback change occurs, we need to look farther and farther back in time. And so the dimension changes and increases. What we find is that we have a torus bifurcation along these vertical lines, connected by border collision torus bifurcations along the horizontal lines as the dimension of the system changes, which is traced back to the symbolic representation of the solution changing. So in summary, we constructed a very simple driven time delay system that nonetheless has some very complicated dynamics. We analyze the system using symbolic dynamics and Poincare maps. The system features a wide variety of bifurcations, and those bifurcations, the border collision bifurcations, are strongly associated with the symbolic dynamics of the system. So I'd like to thank my co-authors, Andrew Keane and Andreas Mann, my PhD supervisors, Andreas Mann and Serka Healy, and the sponsors from my research, the Irish Research Council and the CAPI. If anyone has any questions, I'd love to hear them.
Okay, so thank you, Brian. So there's already one question by Istvan Kish. I read it aloud. So the question is, would similar behavior also exist in smooth systems which approximates the sign function, like, for example, a sigmoid function, if it's close to it?
Yes, yes. So we did look at a very similar system that was, I think you used hyperbolic tan in order to approximate the sign function. And yeah, you've got similar systems, but they would be, slightly deformed from our bifurcation diagrams, and also you wouldn't have such a precise effect of crossing x equals 0 all of a sudden causing problems. It would kind of have to wait a little bit. So yeah, similar dynamics.
So how would the border collision bifurcations, I mean, they don't exist, and they would kind of break up into other stuff, wouldn't they? You don't have a border collision.
Yeah, so the border collisions, they wouldn't happen so cleanly. I suppose they would break up into other things, but you could kind of say that the crossing x equals 0 is still going to be a significant event. It's just that you might have to push a bit further past x equals 0, say, to have your bifurcations occur.
So would you still have a low-dimensional Poincare map?
Probably not, because once you go to the smooth system, then you're going to lose that effect of only needing to know the sign. And so you wouldn't have such a low-dimensional map, I'd say.